Good morning, Applied Physics students. This is Mrs. Krumschreider with some notes and such on Chapter 2, Sections 4 and 5. So we'll be talking about equilibrium of moving objects and looking at vectors. So Section 2.4, which is titled Equilibrium for moving objects. Starts by talking about ways to be in mechanical equilibrium. And when we talk about being in equilibrium, we are talking about a state of no change. So things are not changing. So that's sort of the key thing that you'll look at to know whether or not something is in equilibrium. Okay? So there are two ways to be in mechanical equilibrium. One way is that the object is not moving. Which is called static equilibrium. And in static equilibrium, we still have the fact that the sum of our forces has to be equal to 0, right? That's that equilibrium rule. We can kind of describe this static equilibrium as being a state of rest. And if we sort of kind of look at an example of this, right, this might be where we have a table with an object sitting on the top of it. Maybe it's a book. And we know that there's gravity acting on it with maybe 12 newtons. And so this is our gravity acting on this object and trying to pull it downwards. And so remember, our table has to be providing a 12 Newton support force, which also could be called a normal force. And so because the sum of these forces is equal to 0, because I have 12 newtons up and 12 newtons down, and they're in opposite directions, so I would subtract them, okay? This object is in static equilibrium. And again, static equilibrium is one of the types of mechanical equilibrium. So there are two ways to be in mechanical equilibrium. And again, static equilibrium, our object is not moving, is one of them. Our second way to be in mechanical equilibrium is that our object is moving at a constant speed in a straight line path. This is actually called dynamic equilibrium. So anytime we have an object moving at a constant speed in a straight line path, that's dynamic equilibrium. Now remember, we said that equilibrium was a state of no change. This is a state of no change because we're in a constant speed and we're in a constant direction. And remember, constant really means not changing. Okay, so this is mechanical equilibrium because our speed's not changing, our direction's not changing. Okay, so again, constant means not changing. Again, that means that we have to follow that equilibrium rule, which says that the sum of our forces has to be equal to 0. And it's not really easy to draw a picture of this, but an example of this is when there is a hockey puck sliding on ice at a constant speed, right? If somebody hits a hockey puck on ice, once it's moving at its constant speed, it continues to maintain that speed until there's some other force acting on it to change its motion. Okay, so an example would be a hockey puck sliding on ice. At a constant speed. That is dynamic equilibrium, which is a form of mechanical equilibrium. So, how do you test for whether an object is in equilibrium? So, our test for kind of equilibrium is, does the object undergo a change in motion? And again, a change in motion, okay, means that we have to look at both our speed and our direction. Because, forces have both speed and direction. So a change in motion, do we change the speed of the object? Do we change the direction the object is moving? Then we're going to talk about equilibrium. So does the object undergo a change in motion? No. Okay, if the answer to that question is no, I don't change the speed, I don't change the direction, then the object is in mechanical equilibrium. And again, that might be a static equilibrium, right? It might be a non-moving equilibrium. Or it could be a dynamic equilibrium. It could be a moving equilibrium. Yes, there is a change in motion. Then our object is not in mechanical equilibrium. So that's our test for equilibrium, is whether or not there's a change in my motion, either speed or direction. Now, because we are talking about objects that are moving, right, and are in this dynamic equilibrium, we need to sort of start to become familiar with the concept of friction. Now, friction is a good thing. Friction is what allows you to walk. Friction is what helps keep your car on the road, okay? And friction is a contact force between objects that slide or tend to slide against each other. Right, your shoe kind of slides on the floor and creates friction. Your tires slide on the road and create friction. Your tires slide a little bit less on an icy road, and so there's a little bit less friction. Okay, so friction is this contact force that happens when objects are pretty much when they're in contact with each other. Friction often acts against, or we could say opposite, the direction of motion. So if I have a table and an object sliding on this table, so if this object has a force that's moving it, okay, a net force, right? Because there has to be a net force if the object is moving, a net force to the right, then there is a friction force acting in the opposite direction. It would be less than the net force because that net force is moving the object. But friction is always opposite the direction of motion. So if our object is moving this direction. So again, we will talk more about friction sort of when we get into friction a little bit more, but just so that you know that friction occurs. You saw that on the concept development practice page that we did, the 2-1, that last question with like the pulley and the block and the weight. Okay, they had the word friction in there. So we want to take a look at the page 18 think question. So on page 18, the think question says, an airplane flies horizontally at constant speed in a straight line direction. Its state of motion is unchanging. In other words, it is in equilibrium. Two horizontal forces act on the plane. One is the thrust of the propeller that pulls it forward. The other is the force of air resistance or air friction that acts in the opposite direction. Which force is greater? So there was kind of the little picture. So here's my airplane picture, okay, because I'm definitely a wonderful artist. And I'm kidding, you guys, okay? We saw kind of the vector to the front that was thrust, that was provided by the propeller, and we had the vector to the back, which was the drag, which is that air friction. Okay, and so the question was, which force is greater, the thrust or the drag? And the key here, right, is the fact that we are at, this plane is moving at constant speed in a straight line direction. Remember, that means that we are in mechanical equilibrium. So therefore, we're in mechanical equilibrium. And what has to be true in mechanical equilibrium? Remember, in mechanical equilibrium, the sum of the forces has to be equal to 0. So if my only two forces are thrust and drag, and I'm in mechanical equilibrium, the sum of these forces has to be 0. So that means that my drag has to be equal to my thrust. So it's sort of a trick question, right? Because the question was, which force is greater? And the answer is neither. Oops. Because we're in that sum of the forces has to be 0, so drag has to be equal to thrust. So we know the plane is in mechanical equilibrium because of the constant speed in a straight line direction. Therefore, the drag and thrust forces are equal in size, but opposite in direction. Therefore, the sum of the forces is equal to 0. And this is, of course, a dynamic equilibrium because the plane is moving. It didn't really ask that in the question, but on the tag, I asked you that question. So that's that page 18 think question. All right, section 2.5 was titled Vectors. Remember, we talked about vectors already a little bit. Vectors, a vector quantity has to have a size and a direction. And we already kind of touched on how we go about combining parallel vectors. If those vectors are acting in the same direction, we add the vectors. If those vectors are acting in opposite directions, then we subtract the vectors. And a new term here was the term resultant, which is just what we call the sum of two or more vectors. So just kind of real quick example, right? We did this the other day. We said, here's our object, and there's a force of 8 newtons to the right. There's a force of 6 newtons to the left. And so the question is, what was our net force? Right? And our net force is going to be our resultant, because it's the sum of two or more vectors. And because these are acting in opposite directions, we subtract them. So our net force is 8 newtons minus 6 newtons, which leaves us 2 newtons. And we're going to say it's 2 newtons to the right because our bigger force is acting to the right. So we did this the other day in our notes, and you did this on your tag as well. Okay, so result is just a new term, but it just means that it's the sum of two or more of our vectors. So we have a kind of new rule for when these aren't parallel, which is called the parallelogram rule. And the parallelogram rule says to find the resultant of two non-parallel vectors, construct a parallelogram wherein the two vectors are adjacent. And we'll talk in just a moment about what adjacent means if you're not quite sure what that means. Adjacent sides. The diagonal of the parallelogram shows the resultant. So adjacent means next to each other. So, to sort of look at an example, if I have a force acting upwards and a force acting to the right, if I want to find out what the resultant is of these two forces, I construct a parallelogram. So I kind of make if you have a ruler at home, you might do this with a ruler, okay? Basically, I make a box with, right, this side here is the same length as this side here, and this side here is the same length as this side here. When I do that, then this diagonal is my resultant, which your textbook just calls with a capital R. Another example of that, remember, if you need a little bit more time to write, you always can pause your video, right? So we might also be talking about vectors that are acting like this. I still do the same thing, so I'm going to construct kind of a box, if you will, right? There's my line that's parallel to this one, right? So here are my two parallel lines. Now I need to do another set of parallel lines, right, for this one. So again, kind of over here, right? There's that parallel line. And then my resultant is the diagonal. So that's my resultant. Now notice, okay, that we've formed a triangle. So right, here's a triangle right here. And in this one back here, right, here's our triangle. That means that we can use some triangle math to figure this out if we have numbers for these, right? So, if we have, oops, I'll switch back to my other color. If we have vector A, and we know that it's 2 newtons, and we have vector B, which is 4 newtons, right? We can use this parallelogram rule. So again, I'm going to kind of construct my side. So here's my green side. So again, I'm drawing kind of a dotted line parallel to it, right? Then I'm going to do this side. So here's my parallel to that one. Now I'm ready to look at my resultant, which is the diagonal. So there's my resultant. Okay, which we kind of use a capital R for. So if we want to know the number for this, to find R, you're going to use the Pythagorean theorem. right? And the Pythagorean theorem, you wrote it as a squared plus b squared equals c squared. Now, for us, right, our c, this is our c, correct? So I'm going to kind of just put in parentheses, right? This is going to be our resultant squared. Okay, in fact, we'll do it the other way. Okay, so our resultant is that diagonal, which in your Pythagorean theorem is your c side. So that means then that I can figure this out mathematically, right? A side is 2 newtons squared. The B side is 4 newtons squared, which gives me, I'm trying to get my R, so I have 4 plus 16, which equals 20. Now remember, that's my R squared. I don't want R squared, I want just R. So R is the square root of 20, which is 4.47 newtons. So a way to kind of say that is, if I want to figure out my resultant, I'm going to do the square root of a squared plus b squared. Okay, so again, this is using this idea that we have this triangle, okay, and here's my here's my A side, here's my B side, and my resultant is that C side using the Pythagorean theorem. So this allows you mathematically to do these problems. So hopefully you have a calculator, or you can use your cell phone probably as a calculator, and you know how to take the square root using your calculator. So we sort of did apply this, but we're going to look at applying the parallelogram. Rule. And we want to take a look in your textbook at a couple figures. So figure 211 first. So I'm going to grab that as I have that picture here. It's this one. Okay, so this is that picture from your book. In this picture, the description says, Nellie's weight is shown by the downward vertical vector. Okay, so this right here, this is Nellie's weight, right? That's gravity pulling on her. An equal and opposite vector is needed for equilibrium, shown by the dashed vector. So because we know she's not moving and she's in mechanical equilibrium, the sum of the forces has to be equal to 0. So here is that opposite force. Okay, and notice it's the same length, but it's in opposite directions so that our sum of our forces is equal to 0. The dashed vector is the diagonal of the parallelogram defined by the dotted lines. So what they did again is here's our, right? Here's our opposite force, that support force coming from the tension in those ropes, and they made the parallelogram, right? So again, this side is parallel to this side and the same length. This side is parallel to this side and is the same length. Okay, so they made that parallelogram. Letter C, both rope tensions are shown by the constructed vector. So then what they did is they said, okay, well, now that we've drawn this parallelogram, now we have a representation right, of the tension in those ropes. So this represents that tension. Now, if there were numbers, we could use our Pythagorean theorem to figure out those numbers. But this shows us that there's tension in both parts of that rope. I also want to look at figure 212. So again, I'm going to grab that picture. Okay. So this one says, as the angle between the ropes increases, tension increases so that the resultant dashed line vector remains at 300 newtons upward, which is required to support 300 Newton Nelly. So this still, right, is the weight of Nelly of 300 newtons. And because she's not moving, and because our sum of our forces has to be equal to 0 because she's not moving, this is the support force provided by both sets of rope. It has to be equal in size, right? So the size of these is the same. But opposite in direction. So once I have that, then, and I want to kind of get that out of there, then I construct that parallelogram, right? So again, here's one of the ropes. So here's my side that's parallel to it. Here's my other rope, and here's my other side that's parallel to it. Okay, using this vector. Okay, and then that means then that I know that I could, right, I see the resulting tension in these ropes. Now, what I want you to kind of notice is what happens, like, look at this angle here, right? This is a smaller angle. We could also say that this angle has gotten larger, right? There's a larger angle between this. And what happens to the tension, right? This was the same girl, but the ropes were kind of closer together, right? There was less angle. So notice that as the angle between the supporting ropes increases, the tension in each rope increases. And we can tell that because this vector here is longer than this vector here. Okay? So we can tell that based on that. So we want to take a look at our page 22 think question. And I think there are 2 of them there. So the first one says, 2 sets of swings are shown at the right. If the children on the swings are of equal weight, the ropes of which swing are more likely to break, right? So basically it has a swing set here, and we have the kid on the swings like this, and the kid on the swings like this. And the question is, which set of these, right? The ropes of which swing are more likely to break. Basically, they're asking you which ropes have more tension in them. Right? And remember what we just said. As the angle between the supporting ropes increases, the tension in each rope increases. So this angle right here, right, is smaller than this angle right here. So which set of ropes has more tension? This one. So which one is more likely to break? The one on the right. So the swing on the right, because the angle is greater, therefore the tension in the ropes is greater. Okay? And the second question, consider what would happen if you suspended a 10 Newton object midway along a very tight, horizontally stretched guitar string. Is it possible for the string to remain horizontal without a slight sag at the point of suspension? So they're saying I have a really, really tight string and I hang something on it here. What's going to happen? Is that string going to stay horizontal? No, right? From practice, you should know that as soon as you hang something on that, even if it's really tight, it's going to sag a little bit there in the middle. So that concludes the notes and discussion for Chapter 2, Sections 4 and 5. Have a great day. I'll talk to you tomorrow.